Today, guys, is we're going to start looking at the charge cycle and the discharge cycle for capacitors. And this stuff you might well get like an exam question around some of what we're doing today, but also you're going to do a practical experiment for the assignment. One of the two tasks is around using the discharge cycle and what we know about the discharge cycle of a capacitor to determine the value of an unknown capacitor. And I'm going to be showing you this cycle for charge discharge on a capacitor is very repeatable. It will happen exactly the same way time and time again, so we can use that solid knowledge we know about that to do an experiment where we discharge some capacitors and then use some calculations to work out what the practical value of the capacitor is. Okay, and see if it come within the tolerances of the nominal value of that capacitor. Right? So, first of all, we need to make some rules. What we're going to be talking about this morning is we're going to be talking about voltage and current and at an instant in time. We're going to be talking about instantaneous values. And when we use instantaneous values for current, voltage, and really on any other varying engineering quantity, but in this instance current and voltage, lowercase letters are used. And what we do is we say for voltage we use capital V for the maximum value, we use little v at time t for the instantaneous value. And that notation, sometimes put a little VM beside that for max, okay? And then for current, similar, IM, maximum value, little I at time t is the I suppose really I should qualify these two at t seconds. So we'll eventually have formulas for the instantaneous current and the instantaneous voltage, both during charge and discharge, okay? And they will allow you to calculate what the voltage or current is at an instant in time, based upon starting at 0 seconds, okay? So this one should be at t seconds too. Yeah. And that's really important that if you get a question on this, that you use that notation correctly. You use uppercase letters for maximum values, peak values in AC. You use lowercase letters for instantaneous values that are changing with time. Okay? Right, everyone happy with that? Yeah? So, what we'll have a look at first then is capacitor charge. And all we know at the moment, right, is from what we did last week, is we apply 10 volts to a capacitor, and I said there is a short transient period, but eventually it will charge up to 10 volts across a capacitor, and you take the voltage away, and if the capacitor is perfect, it will remain charged. Nothing's perfect, so it will remain charged for a period of time. Eventually that charge will leak away. So we're all happy with that. That's what you know up to now. So what we're focusing on this week is that short period that it takes to get from 0 volts to 10 volts, if that's the applied voltage. Okay? So if we, if we start our analysis with our circuit, and we're going to have a resistor and a capacitor in series. Okay? I'm going to have a circuit with a switch in it. And I'm going to have a 10 volt source. Okay? I'm trying to create a left and a right side to my screen because I'm going to keep altering the circuit as we go down and gradually drawing a graph of what's happening when it charges up. Okay. So what we want to do is focus on what happens with this circuit from the instant we turn that switch on and apply that 10 volts to the circuit. Initially, how many volts across the capacitor? Before we turned it on, how many volts was there? 0. So at the instant we turn it on, 0 volts. Yeah. Therefore, by try and use different colours here, Kirchhoff's voltage law. What's VR? What does Kirchhoff's voltage law say about a circuit loop? Which way would, if that's the plus end, which way would we put an arrow on there? Clockwise. Yeah. So that 10 volts is that way. We've got 2 arrows going anti-clockwise. One of them's nothing. So what's that one? Okay. So at the instant we turn on, we're going to get 10 volts drop across the resistor. Nothing currently, no charge on the capacitor. All right. A current, little I, will flow. We're going to call this little v, that's the voltage across the capacitor. Okay, little vc. We'll call this little VR throughout this process of looking at this cycle. Alright? And for the time being, I don't need to worry too much about the capacitor value, but our resistor can be 10 ohms. What I'm going to do is draw a graph axis, seconds there, and this axis can be, I'm going to use it to represent little VR in green, little VC in red, and little I in blue. Yep. Okay. So, little VC at time 0 is nothing. Put a dot there. Little VR at time 0 is 10 volts, so we'll label that 10 volts at the top. Okay. Current. How can I calculate the current? V over R. Which V? What's controlling the current in this circuit? Yeah, no, but what is controlling, sorry, the level of current in this circuit? The resistor. So we got to use VR and the value of the resistor all the time. Remember, no current can flow through the capacitor at all. All we've got is charge or electrons going this way around the circuit and building up on that plate. So we've got electrons leaving that plate and going around and touching that plate. No current flows through that insulator in the capacitor, does it? Yeah. So at the instant turn on, I, little I, must be the 10 volts over the 10 ohms, 1 amp. Everyone happy with that? So in terms of current, I'm going to make this dot up here also. In fact, what I'll do is I'll reduce the current axis a little bit. I'm going to make 1 amp in terms of the current there. I want to put all these things on one graph, you see, and I'm going to keep them away from each other. So that's where they start, at the instant we switch on. All right? Everyone happy? Yeah? What we're going to think about now is, after a short period of time, t seconds, after a second or two maybe, depending on the component values, as you're going to find out later, our capacitor voltage has gone up to 2 volts. So a current's been flowing and the capacitor voltage has reached 2 volts. Okay, so let's try and estimate that on our graph here. After a short period of time, there's 5 volts about there, so 2 is going to be about there. Yep, happy with that? What's the voltage VR going to be now? Yeah, because we've got to make 10, so it must be 8 volts and 2 volts. So VR's dropped a bit, like there. What about the current now? Yeah, the current becomes 8 volts over 10 ohms equals 0.8 amps. So if less current's flowing, the charge is moving less quickly, the capacitor is charging up slower as it goes on. Because if the current's reducing, it's not going to charge so quickly. So our current goes from 1 amp down to 0.8 of an amp in the same time. Yep. Capacitor voltage has risen to 7 volts. What would be the resistor voltage now? 3. Okay. And the current? 3 volts over 10 equals 0.3 amps. Okay. So in another period of time, our VR has fallen down to about 3 volts there. Okay. Our current has fallen to 0.3 of an amp. Let's make that down there somewhere. And our capacitor voltage has risen to 7 volts. Yep. Okay, see, getting what's going on here. Because the capacitor voltage is rising, the resistor's got less across it, less current is flowing, so the rate of charge is reducing all the time. That's why we get a curve. We don't get a straight line, we get a curve. Alright? One more. Capacitor voltage to 9.5 volts. Resistor voltage .5 volts. Current .5 over 10, 0.05 amps. Okay, so that would happen after a longer period, considerably longer period of time, because remember the current's reducing all the time, so the rate of charge is reducing all the time, and so on. So we'd end up with a current down here somewhere. A resistor voltage tending to 0 as well, and a capacitor voltage is 10, about there somewhere. Tending towards that 10 volt line. Okay, but as you'll come to find out, it never actually gets there, because the current never really reaches 0, but it becomes so small that you can't measure it. The distance the capacitor voltage is away from 10 volts becomes so small that's hardly measurable, and the volt drop across the resistor becomes so small that's hardly measurable. But the formula for it says that capacitor voltage can't reach 10 volts precisely, the current can't fall completely to 0, and the resistor voltage can't fall completely to 0 either. But to all intents and purposes they do. And there is a point in that cycle where by convention we say the capacitor is fully charged, and at that point I think that's something like, we'll calculate it later, but I think that's something like 99.5% towards that full 10 volts if that's what you're applying. Okay, so that's what's going on during charging. Gradually, as the capacitor voltage increases, there's less voltage across the resistor to push current around the circuit, so the rate of charging of that capacitor is falling all the time. We get that kind of shape with the capacitor charging voltage. Alright, all happy with that? Now, that is a Greek letter tau. It's a symbol used for the time constant. For a CR series circuit, which is what we had, a capacitor, a resistor in series, tau is equal to C are seconds. So we multiply the value of the capacitor by the value of the resistor, and we get the time constant. What I'm going to do now is explain in graphical terms what's meant by the time constant. T in seconds. Yep. VC, the capacitor voltage in volts. Okay. And here's our V max, 10 volts. And I've already seen what the go ahead, divide this up a bit. 1, 2, 3, 4, 5. That's the kind of shape we get for charging. Okay. And I'll tell you now, it's really important that you get this theory, because you may well you could get questioned on the theory and the description of this time constant thing in the examination. You could do. All right. You do get them on paper, yeah. The maximum, that's what we're applying, so that would be the battery voltage jack in the circuit that we had before. Okay? And you notice I've drawn my curve, so that's not quite reaching 10 volts. Okay? And the little 5 ticks will be explained in a minute. Okay? Now, if I was to, let's imagine we got our previous circuit and our initial current as 1 amp. Right, so if we kept applying our initial 1 amp, so we'd done something to the circuit electronically, so that every time the current fell a little bit, we added a bit more in to keep that current flowing. The only way we could do that is regulate it by increasing the voltage. Okay, if we kept it at 1 amp instead of allowing that current to drop, we'd rise up here like this, okay, and carry on going. And that capacitor voltage would travel beyond 10 volts. Alright? But if the initial 1 amp is caused by applying 10 volts, then it would hit that 10 volts there in CR seconds. The time constant is the time it would take the charge to reach the initial applied voltage if you keep a constant current. Alright? Yeah, if you keep pumping 1 amp in, Lewis, your voltage will keep rising. The problem there is your capacitor is going to have a working voltage, and once you go above that by a significant amount, boom. Right? Okay? But in certain electronic circuits, they use that to create this ramp. If that's what you want, an increase in voltage at a certain rate, you can do that by applying a constant current to a capacitor, and that's used in analog to digital conversion as one particular use I know of, for having a constant current source so that you can create that ramp by charging a capacitor. Okay. So it would reach the 10 volts, and that's how time constant is defined. In this sense, what you'll find through calculation later is after CR seconds, that point there, it actually gets to about 67% of VM. So about 6.7 volts. Yeah. And then after one more time constant, because the slope is reduced, so that's 2 CR, 2 time constants, it'll move another 67% of the distance between there and the top. It's a very repeatable thing. So if the difference there is 3 volts, it'll move another 67% of 3 volts in the next time constant. That's why I can't, no. 3 CR, 4 CR, 5 CR. And what you'll find through calculation is approximately, certainly over 99.5% of its VM by the time you get to 5 constants. So the rule of thumb is 5 time constants, capacitor is fully charged. So now on kind of rule of thumb industry, we'd say it's fully charged after 5 time constants. If initial rate of charge, I'm going to put in brackets current, is maintained then capacitor voltage will reach VM value in CR seconds. 1 time constant. Yep. All right. Everyone happy? That is very, very, very repeatable. It will happen time and time again. Of course, if your capacitor is partly charged when you switch it on, which it could have a little residual charge in it, and it's going to be going between that voltage and what you're applying. But that ramp up there is repeatable time and time and time again under the same conditions. Yeah, what you're going to do is for each time constant after the first one, you're going to travel 67% of the distance between where it is and where it's heading. Yeah, because as you can see from that, the slope, thinking rate of change situation here. So the slope dy by dx of that graph is reducing all the time. The current flowing is reducing, so the rate at which it's charging is going to be reducing all the time. So it can never quite reach that 10 volt line, but it gets close enough that we consider us there. Yeah. Gets to about 67% after 1 time constant, and we'll calculate it so you can see that shortly. Yeah. 6.7 volts. That's how far it will move in the next. So you'll add that on to your 6.7 volts. Yeah. And so on. Yeah. Yes, yes. All right, every step it'll move 67% of the way between where it is and where it's heading. Okay? So, gentlemen, what we've got is a graph that looks like this, the capacitor charging. VC time in seconds. What shape of graph is that? What kind of function is that? Anyone, any ideas? Sorry? What, lnx? Why is it lnx? Is that what you're saying? Yeah? Okay. That looks like the current one and the voltage across the resistor. Yeah. Exponential decay. So the negative sign makes it decaying. So starting high and it's decaying, never quite reaches, and you'll see why shortly, never quite reaches 0. Okay. So we've found a way that we might be able to define the resistor voltage and the current during charging. Okay. The other one, Y is equal to 1 minus E raised to the minus Kx. What's going on? Something I've done wrong. No, it isn't. Oh yeah, because the negative, I'll put a minus in. Yeah. Let's make that a different constant. V. There we go. Purple one. Okay. Y is equal to 1 minus E to the minus a constant x times x. Exponential rise to a limit. That's what that is. Okay. So I'm going to go back to this now. What we have for that charging period is that VC at time t is equal to Vm times 1 minus E to the minus t over CR. The constant that I put in those formulae on the graphing software, the constant is 1 over CR. So the time constant will control whether that's a steep curve or a shallower one. That's where I go in the formula. The way this formula works is that this bit is always worth a little bit. Okay, that can never be 0. That, no matter how long we go on for, that bit, e to the minus t over CR, will never be 0. Therefore, although we got Vm there and we got 1, we're always taking a little bit off 1, and therefore the result of that is that the capacitor voltage will always be a little bit less than 10 volts. Yep. I put just that in with a minus KT. I just put the basic version of it. This is the actual electrical version showing you that that constant is made up of, so the constant K that I put in the other graph here is equal to 1 over CR. And that's X, so that's, and that's minus. So you end up with minus T over CR. Right? Here's our VR, little VR at time t is equal to Vm e to the minus t over CR. Alright? So again, because that's always worth a little bit, that's always going to be a little bit times Vm, and therefore the answer to that can never be 0. Can you see that? Because e to the minus t over CR can never be 0, then the whole thing can never equal 0. Right? And then lastly, in blue, our current I at time t is equal to I'm going to label that the initial current okay, times e to the minus t over CR. What is the what? That's the capacitor voltage at an instant in time. So that's a lowercase v. Dom. That's little VR. That's the resistor voltage at time t. And then our current's got no C or R with it because that's the same current for both components. Okay, you all happy? Yep. Minus what? Yeah. That having that bracketed term gives you the shape that is a rise to a limit. If you'd have the same as these. So what you're saying is yeah, that's the only reason. Then you put the bracketed term, otherwise you'd have to write Vm minus Vm times that. So you take that common term outside the brackets. Okay? All reasonably happy with that, yeah? Right. Let's have a little circuit and do some calcs, shall we? 10 ohms, 0.1 farads, a switch, 10 volts, first thing we'll do is find CR. We'll find VC after 1 times CR and find VC after 5 times CR. And we'll find I after 1 times CR as well. CR. or the time constant. Tau is equal to C times R, 10 times 0.1, 1 second. I keep it nice and simple for the first example. So the capacitor voltage after one time constant, Vc, is equal to 10 volts times 1 minus E to the minus 1 over 1. Time constant's 1 second. Yeah. Equals. Plug that in your calculator and you should find that 10 times 1 minus E to the minus 1 gives you 6.7 volts, 6.3 volts. I lied, 63%, not 67%. Here, Vc is 10 times 1 minus E to the power of minus 5 over 1. After 5 time constants, so after 5 seconds. Do that one. I believe you'll get 9.99 volts. Okay, call me a liar for a 0.06 of a volt. Alright, but you get my point. After another second, that'll be 63% of the way between 9.932 and 10, i.e. not very much. Okay, so that point there is considered to be fully charged. To all intents and purposes, fully charged. Okay, and then lastly, I, after one time constant, is equal to Im E to the minus 1 over 1. And what's Im in this case? It's initial current, 1 amp. So it's 1 times E to the minus 1 equals. .37. Right, it is fallen by 63% of its starting current. See how consistent that is? Right, everyone happy with that? Now, what I'm going to do now is look at this type of question. Find the time when little Vc is equal to 5 volts. Okay, same circuit for the previous circuit. I'm getting a bloody stitch reaching up there. Find the time when little Vc is equal to 5 volts. we've got this formula, Vc is equal to Vm times 1 minus E to the minus T. And I'm going to keep the time constant CR, I'm going to write it as tau for now. Okay? That'll just keep the two things together. What we got to do is we've got to rearrange that formula so that we got T equals something. Where are we going to start? Divide by Vm. So we get Vc over Vm is equal to 1 minus E to the minus T over tau. Next. Sorry? You could subtract the 1. Okay? What would you be better doing and why? If you subtract 1, what's left on the right hand side? Minus E to the power of minus T over tau. So you could, an alternative is to add E to the minus T over CR or over tau to the other side. So if we plus, keep what we're doing in, add E to the minus T over tau, both sides. So we end up with this on this side, little Vc over Vm plus E minus T over tau is equal to 1. Next operation. Remember, it's T what we want. No, that we wouldn't do that, Lewis. No. Yeah, take away the Vc over Vm. So we end up with E to minus T over tau is equal to 1 minus little Vc over Vm. What's the opposite? How do we get rid of E? Look at your calculators. Ln. Proper name, natural log. Yeah. Ln of both sides. So if we do the natural log of that, the E disappears, and we end up with minus T over tau. We've got to take the natural log of everything on this side. Times everything by tau or CR if that's what you want eventually. So we end up with minus T is equal to tau times ln 1 minus little Vc over Vm, like so. But we got minus time. So what do we do? Yeah, effectively what we're doing is multiplying. So let's just write this, what we done there. That was ln of both sides multiplied by tau. Here we're going to, effectively what we're doing is multiplying both sides by minus 1. So we end up with T on this side is equal to minus tau ln 1 minus little vc over vm equals. And you notice the best efforts I make to make a distinct difference between my lowercase and uppercase v's. That's the way where you could lose 1 mark in an exam, that is. There's a distinct difference between that one's the worst one. Capital V, right? Lowercase v. I'm going to usually try and do them like that or something. You should be using uppercase and lowercase letters.
Yeah, but the thing is a V and a V. It's a V. And I can depend on the like the C and the C.
So now what we can do is put our numbers in. T is equal to minus 1, because that was our time constant, times ln 1 minus VC was what we're looking for when that's 5 volts, when we're applying 10 volts. That'll give us time when the capacitor voltage is equal to, where are we expecting it to be with a time constant of 1 second? Less than a second or more than a second? Stop, don't push your buttons yet. Less than a second or more than a second? You're applying 10 volts. We're looking for the time when it gets to 5. Now on what you know about the time constant, are you expecting this to be less or more than 1 second? Yeah, because 5 volts is not 63% of 10, it's going to be less than a second, isn't it? It's a useful thing to think about. It gives you an idea of whether you're in the right place. Exam question. Does my answer make sense from the electrical knowledge that I know? Yep. So what is the answer then? 0.69 seconds. Does that match? Yeah. Okay. And this repeatability of this charge-discharge thing, because the discharge is just as repeatable, is why capacitors are used quite extensively in timing circuits, because that's a very repeatable thing that you can measure. All right? Well, if you had to do that, well, that'd be part of a whole question about if there's a 20-mark question, you'd probably get 6, 7, 8 marks for that bit. 100 marks in the paper, yeah, usually. 1 hour paper.